Alright, in this tutorial we're going to go over how to factor quadratics, but a special case to make it a little bit easier in order to factor a quadratic expression. So this special case is called the difference of perfect squares. Now if you have two terms that are perfect squares, that means if you take the square root of that number you get a whole number, and they are being subtracted, that means that you can factor each one of those terms into an a plus b and an a minus b. Now, if you look back into our last unit of multiplying binomials of a special case, this is actually the complete reverse order of the difference of perfect squares, where you have two identical binomials. The only difference is one of them is being added, one of them is being subtracted, and you end up with your a squared minus b squared. This is the same thing, but just working backwards, where you have a perfect square term in both your first and second position, and the two terms are being subtracted. So some common perfect squares that you need to be familiar with are you just go into 1 through 12 squaring each number. And you multiply each number of that by itself. You need to at least be familiar with. So obviously 1 squared is 1. 2 times 2, 4. 3 times 3, 9. 16, 25, 36. That's 6 squared, so 7 squared is 49. 8 squared is 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. And 12 squared, 144. You at least need to have, at a bare minimum, these perfect squares memorized, that as soon as you recognize these numbers, you should automatically think, okay, this is the difference of perfect squares. I'm going to take the square root of each of these and get an addition and subtraction binomial. So this first example, 9d squared minus 25. Both of these terms are perfect squares because you have a 9d squared. Anything that has an exponent that's an even number is a perfect square, and a 25 by itself is a perfect square. So we're going to end up with two sets of parentheses. If you take the square root of 9d squared, the square root of 9 is 3, and the square root of d squared is just d. So that is going to be your first term in each of your binomials. Then you're going to take the square root of 25. That's going to give you 5. And one of your binomials must be plus, one of them must be subtraction. Now the order does not matter. You could have your subtraction binomial come first and your addition binomial come second. Since they're all being multiplied together, it does not matter. Now you may run into some binomials where these numbers themselves are not perfect squares. However, if you factor by GCF first, you will end up with perfect squares. So 128 itself is not a perfect square. However, both of these numbers can be divisible by 2. So if we factor out 2 from each of these terms, we are left with 64 u squared, and 162 divided by 2 gives you 81. And both of these numbers are perfect squares. So when you take the square root of 64 u squared, you're going to end up with 8u as your first term in each of your binomials. Then the square root of your second term, which is 81, gives you 9. 1 is plus, 1 is minus. And that 2 stays out in front of everything, and there are 3 terms that are all being multiplied together. So even though you may not recognize it right away, sometimes you may have to factor out by GCF first, right here with this 2, in order to get your scenario of the special case of the difference of perfect squares.